All right, hello everybody. So today we're going to be covering the information found in chapter 4.5, which is on exponential equations. All right, so as before, when we're talking about equations, that's just one thing is equal to another thing. We're solving for the unknown values. But in this case, right, we're talking about equations that have exponentials in them. All right, so the first thing that we're going to need to know, and this is just sort of a reminder from last week, is the relationship between the exponential function and the logarithmic function. Okay, so if we let f of x be equal to a to the power of x, right? So the exponential function with a base of a, and we let g of x be equal to log base a of x. F and g are inverses of each other. Right? This was covered in Tim's videos from last week. Right? We know that f of x is a one-to-one function, so there exists an inverse, and then we basically just defined log of a such that it is that inverse, right? But so what this tells us that f and g are inverses of each other is that if we take f and we compose it with g, right, which is just f with g of x as its argument, right, this is going to be equal to, we're going to take that a of x, but instead of the x, we're going to have g of x, which is log base a of x. This is going to be equal to just x, right? And that's because, once again, f and g are inverses of each other, right? It also means that if we take g, compose that with x, g composed with f, right, which is g with f of x as its argument, this is going to be equal to log base a of x. That's going to be equal to x as well, right? Both of them are just the identity. We're sending x back to itself, right? So we can use this when we're solving different kinds of exponential equations to eliminate either the logarithm or the exponent from the equation that we're working with, okay? Or at least from the part that has the unknown variable in it. All right, so let's look at an example to hopefully make everything a little bit clearer. So in this case, our example is going to be we're taking e to the x minus 4, and we're going to let that equal 16. Okay? So we want to try and basically isolate our x variable so we can know what values of x are going to satisfy this equation we've set up here. Right? So the first thing that we're going to do is we're going to apply this second rule here that we were talking about, right? If we take log base a of a to the x, it's just going to be equal to x, right? So in this case, our base is e, so we're going to take the natural log of both sides of our equation. So we're taking the natural log of x minus 4. It's going to equal the natural log of 16, right? And so I'm going to use a rule here that we have for exponents really quick, or for logarithms, my apologies, right? So if we have an exponent inside of our logarithm, we can just take that exponent and multiply it out front, right? So this here is going to be x minus 4, and then we're going to be left with just the natural log of e, right? And that's going to be equal to the natural log of 16, right? But the natural log of e, right, this right here, that's just equal to 1, right? So what we're going to end up with here is we're just going to have x minus 4 is equal to the natural log of 16. Sorry about the handwriting there. It's kind of new to using this whole iPad thing. All right. But so we have x minus 4 here, so we can take x is going to be equal to 4. And I'm going to kind of use the same trick with this 16 over here inside the natural log. We can rewrite 16, right, is equal to 2 to the power of 4. So we can multiply that 4 outside of our natural logarithm. So we get the 4 here, and then we're left with just the base inside, which is going to be that 2. Right? So x is going to be equal to 4 plus 4 times the natural log of 2. All right, and that is the value for x, which satisfies our equation there, right? So I'm just going to write down some general guidelines here for how we're going to solve equations of this sort. All right. So step number one, we're always going to want to isolate our exponent, right? Our exponential part. Right? In this case up here, when we were doing that, right, our exponent, which is this part right here, right? This is our exponential part for this equation. That's already isolated. We didn't have to do anything else there, right? But normally you want to isolate that first. And then we are going to take the log of both sides. And then finally, our last step, right, is we just solve for our x. All right? 3 simple steps, pretty straightforward, right? Isolate, take the log of both sides, and then solve for our x. All right? So let's do another example that's a little bit more complicated, and we'll follow the steps there, okay? So, example 2, right? So, in this example, oh no, how does that keep happening? All right, so in example number 2, we're going to take e to the power of x plus 2, and we're going to set that whole thing equal to 7 times e to the x squared, okay? And we want to solve this for the values of x that satisfy the equation, right? So the first thing that we're going to do, just as before, is we're going to isolate our, or we're going to isolate our we're going to isolate our exponential expression, all right? So in this case, I'm just going to move this term. Let's use green this time. We're going to move this term e to the x squared to the other side of our equation, right? So we need to multiply both sides by something that cancels out with our e to the x squared, right? In this case, that's just going to be e to the negative x squared, right? When we multiply exponents with the same base, we just add our exponents, our powers, right? Which will be 0. E to the 0 is 1, so that's going to cancel out, and we'll just be left with 7 on this side. Also going to do the same over here. E to the negative x squared, right? And so what we're going to get is we're going to get e to the negative x squared plus x plus 2, right? Once again, just using the rules of exponents. That's all going to be equal to 7, right? So now we have the exponential expression isolated on the left-hand side of our equation, right? So now we can take the natural log of both sides. So we're going to get the natural log of e to the negative x squared plus x plus 2, and that's going to be equal to the natural log of 7. And just as before, all we're going to be left with is the power of our e there, right? So this whole thing is going to be negative x squared plus x plus 2, and that's going to be equal to the natural log of 7, right? And so we're almost to a place where we can start solving for our x values, but first we're just going to move this natural log of 7 over to the other side, right? So we're going to get negative x squared plus x plus 2 minus the natural log of 7, and that's going to be equal to 0, right? So what we have here is we have a quadratic that we've set equal to 0, and so we can figure out what our values of x that satisfy this are by using the quadratic formula, right? So in this case, it would be negative 1, which is our negative b value, plus or minus the square root of b squared, 1 squared. And then we're going to have minus 4 times negative 1 times 2 minus the natural log of 7, right? Let me check something really quick. All right? And then this is all going to be over -2. All right? And so we can just plug that into a calculator and find what values those will take. All right? I'm not going to do it here, but that's the process that we're going to take. Okay? So the neat thing about all of these steps that I was just talking about in this process is that we can also apply them to logarithms, right? The same basic process is going to work. We're just going to replace the exponents with logarithms, right? Which, remember, logarithms basically are exponents, right? They're just a different way of writing them. All right, so we're going to do the same thing, but with log. All right, so let's just do another example. I think this is example number 3 that we're doing here, right? So we're going to have log base 2 of x plus 2, and we're going to set that equal to 4, all right? And we want to solve for the value of x that satisfies this equation, right? Okay, anyways, so we know that if we take 2 and raise it to the power 4, that is going to be equal to 16, right? So what we can do is we can instead say that 4 is going to be equal to log base 2 of 16, right? We just rewrote our 4 so that it's in terms of a log base 2, right? So we've got log base 2 of x plus 2 is equal to log base 2 of 16, right? Which is the same thing as 4 as we just discussed, right? And so what we can do here is we basically just take our 2 and we make the equations as we have be the powers of that base 2, right? So since we have we're not changing the powers, or we're not changing the equation, we're just making them equal to each other in the powers, right? So 2 to the power of log 2 times x plus 2 is going to be equal to 2 to the power of log 2, log base 2 of 16, right? And so what we're going to get is we're going to get that we're going to have our x plus 2 is going to equal 16 here, all right? Which means that our x is going to be equal to 14, right? We just take 2, raise each part of the equation to that 2, and then it'll cancel out with our log 2's, leaving us with this x plus 2 equals 16, right? We can also do this in another case, right? So just another example here of where we can use this. We're going to take the natural log of 4x squared plus 3, and we're going to set that equal to 3, right? So we've already got our natural log isolated here, right? So we just need to take each side of this equation and take e to that power, right? So we're going to take e to the natural log of 4x squared plus 3, and we're going to say that whole thing here is going to be equal to e to the power of 3, right? Right? So that e and the natural log, they're going to cancel each other out, and we're going to be left with 4x squared plus 3. And that's going to be equal to e to the power of 3, right? So we get 4x squared plus 3 minus e to the power of 3 is equal to 0. And once again, we've got a quadratic here, and so we can apply our quadratic formula. Right, no problem. Just identify your A, B, and C and plug it into the formula and chug. All right. So before we are done for today, I want to look at an example that we can use in the real world of this kind of situation, okay? So we're going to be looking at continuously compounded interest, all right? and how we can use the solving equations to answer questions about continuously compounded interest. All right, so just in case we don't remember what that formula is, we're going to let A of t, right? So this is the amount of money that is in our bank account after time t, is going to be equal to the principal amount that we have invested times e to the power of rt, where r is the rate at which we are, the interest rate, and t is the time that it's been left in the bank account, right? Oh my gosh. All right. So we're going to look at a specific example where the principal amount we're investing is going to be equal to $1,000. And we're going to say that our interest rate, R, right, our annual interest rate is equal to 3.1%. Okay? And so the question that we're trying to answer here is, how long do I have to leave my money for the amount to double? Okay? So we want to answer that question, right? So let's sub in the P and the R that we have for our continuously compounded interest function, right? So A of t is going to be equal to 1,000 times e to the power of 0.031 times t, right? So this represents, if we plug in an amount of time in years, how much money will be in our bank account after that much time, right? So the amount of money that we're looking for in the bank account is going to be when A of t is equal to 2,000, right? Twice the amount that I started with. So what we're going to do is we're just going to create an equation by subbing that 2,000 for A of t, right? So 2,000 is equal to 1,000 times e to the power of 0.031 t, right? And then we're just going to solve this equation using the techniques that we've learned above, right? So if I divide both sides by 1,000, right, these are going to cancel out, and we'll be left with 2 is equal to e to the 0.031 t, right? And now I can take the natural log of both sides of my equation here, right? So we get the natural log of 2. The natural log and the e will cancel out. We'll be left with 0.031 t, right? And then my last step is I just divide both sides by that 0.031. Right? And then that will approximately equal, let me just plug that into my calculator really quick. We divide that by, it's going to be approximately 22.3 years. Right, so maybe not the best method of investing your money, right? It's going to take you 22 years to double the amount of money that you have. Okay, so that is it for today. Next video, just to give you a look ahead to what we're doing next. Next video, we are going to cover chapter 4.6 this time, right? And we'll just be looking at different ways that we can use these kinds of exponential functions to model situations in the real world. Okay? So thank you for watching. And yeah, have a nice day. Thank you.